So, last time we just were moving on to talk about priority-driven scheduling. So we're going to talk a little bit about scheduling today, then I'm going to go over a bit about the labs that most of you all have been working on. Hopefully it'll be of some help or help you understand in greater detail what you've been trying to achieve, and perhaps give you some hints of answers for those who've been struggling a bit. In terms of priority-driven scheduling, so this is the easiest type of scheduling there is, where you just give every process a priority and the CPU goes to the highest priority. So this is what we've been talking about using within microCOS2. Of course, we can have different types. We can have either a fixed priority or a time-varying priorities. Time-varying is obviously more complex, but there's various advantages to that in terms of meeting deadlines. This is something that we'll compare further on in the course. We'll give you some examples of scheduling methods that can change priorities and see the advantage of doing this. Of course, the cost is you need more time with the operating system to sort out the priorities. Okay, so in terms of fixed priority scheduling, it's best to just give you an example. Now you should be able to walk through this trivially yourself, but we'll go through it together. So we've got three processes, each has a fixed priority. Priority 1 is the highest, following what microCOS2 does. Highest priority gets the CPU, and processes continue until they're done or wait state. They're all periodic processes. Okay, so remembering these processes, we've got a little diagram. So I think P1 has a 10 seconds, P2 has 30 seconds, and P3 has 20 seconds. So given this time schedule, what's going to happen? So the first thing you need to know is what is currently in my ready queue. Which tasks do I have to choose between? So at T0, by chance, P2 becomes ready. Given that there's nothing else in my ready queue, and my OS goes, okay, run P2. So I run P2 for a given amount of time. So here I've run it for about 15 seconds. And the reason I've stopped there is because P1 becomes ready. So P1 becomes ready. Which do I select? P1, yes, P1, I hope. And so P1 runs. At some point, P3 is going to be ready at time 18, obviously because P3 is a lower priority than P1, then P1 still takes the CPU. What happens here? Why is P1 stopped running? It's finished, yeah. 10 seconds it runs. So then P2 comes back in because it's higher priority than P3. At this point in time, P3 is completed, P2 is completed, so P3 can take the rest of the time. Very simple. This is what you're thinking about when you're creating your tasks during your labs. Okay, so what is the scheduling problem? The key question that all of this is trying to answer is, can we meet all our deadlines? The second question is a different way of phrasing the same question. How much CPU horsepower do we need to meet our deadlines? So if we're not meeting our deadlines, what options do we have? We can kill some processes. We can buy a better CPU, which runs faster and gets our jobs done. So if you can get away with a cheaper CPU, then it's great. And so you want to use as little as possible. And this is where you need your statistics tasks to understand CPU usage and whether you can meet all your deadlines. So in terms of processes, generally in this course we're only going to be talking about periodic processes. So these execute with a given every certain period, they run for a certain amount of time, and they have to complete within their period. Aperiodic processes execute on demand, and The reason we're avoiding them is because they're much more difficult to analyze. So if you imagine, say I had some process, so P1, say, has regularly running for a given amount of time. So you can see it's got a period, a regular period, and then a certain runtime. If I had a second process, P2, let's change the color, say it had a longer runtime, but it needed to run less regularly, so it needs to run twice in this time period. Can you schedule this to meet all deadlines? Well, you could imagine what would happen is if I say P1 is the higher priority, I can run P1, then I'm going to run P1 whenever it happens because it's a high priority task. And then I can run P2 in the interim. So P2 will run in this section and in this section. What else have you got? What are the gaps? They're basically your spare time, right? Nothing's happening in this time. So you can imagine checking whether this thing with periodic processes meets all their deadlines. You can see that all the deadlines are met. So P1 finishes before each deadline, P2 finishes before the deadline, which is when it has to next run. If you had aperiodic processes, well, you have to say, well, what is the worst case? The worst case is if they all happen to come at this point in time, will they all, if they all arrive at that point in time, will they all finish by their deadlines? You don't know. It's much harder to analyze, so we conveniently ignore this. In terms of just notation again, so we've talked about a period, so that's the interval between activations. Your rate, which is how often your processes have to start, is just 1 over your period. So we've talked about this here. This is your period. It has to, but your rate is it starts here, it starts here. Sorry, that's your initiation time. When they become ready. Your deadline is when they must finish, and we're treating deadlines as just when the process has to begin its next period for now. Okay, so what happens if a process doesn't finish by a deadline? And the answer is it matters. The question is whether it's a hard deadline or a soft deadline. So, can anyone give me an example of a hard deadline? In any kind of operating system? Say I'm flying a jet fighter. These are pretty cool actually, because if you may or may not know that these fighters are actually designed to be unstable, and that allows them to turn quicker, maneuver better. Of course, that means you need a computer to control your system. If that computer misses deadlines, what's going to happen? The controller's not going to work properly, someone's going to die, someone's going to get angry, maybe. Soft deadlines. Who can think of an example where you have a soft deadline? Or a task sorry? Yeah, so internet is a good example. So if you're watching a video or something, right, you want to, it will have its time to meet, but if it becomes a bit jerky or you miss a few pixels here or there, you're probably not going to notice it anyway. If it happens a lot, then you will. So there are times when you have hard and soft deadlines, and this is when you have embedded systems. You make sure you meet all hard deadlines. Right. So, and here is an example, someone else, of where you can. There's tons of these famous examples where people have failed to meet deadline. So in Space Shuttle's first launch, you had two control systems which had to communicate with each other. They had to synchronize together, and someone did a bit of software code change. Didn't check it carefully, it missed the timing. There was low odds of this problem actually occurring. Well, actually, I would say that's pretty high odds of occurring, but it might not have occurred in their few random tests beforehand, and it caused an expensive launch delay. And I'm sure there's a lot of more worse examples out there in the space if you look around. But anyway, so now I wanted to talk about this stuff about the lab and about timing. So this is a different set of notes. Speaking about notes, I have had a few requests to get them up earlier. I haven't changed much today. I've just added a slide or two. But for future weeks, I'll try and make sure they're ready by the start of the week. Okay, so if we're talking about our statistics task, statistics are all based on the timer, because we need to know relative to some form of time, so we need this timer interrupt. So why do we need a timer interrupt? Well, how have we used it? We've used it for sleeping and waking. So this is when we type in OS time delay, or OS time delay, hour, minutes, seconds, milliseconds. Our process goes to sleep. So why do we need the timer interrupt? So that it wakes up at a certain point in time. If we don't have it, then it's pretty hard to use. So it allows sleeping and waking. It also allows a timeout, so you could imagine that if you've got a process which is really low priority, it's waiting for some runtime, and then it's waited for so long and never got the CPU, that some high priority process just goes away and kills it. So you can have time ups. Again, we need to know some concept of time, so we need the timer interrupt. Speaking of time, you can actually use it to actually keep time and write a clock. But really what I should say is, we've got all these answers here. The key answer to me is, why does an RTOS need a timer interrupt? This is for sharing the CPU, which is what we've talked about before. You can share it with other ways. You can voluntarily send your task to sleep, but a much easier way is just to say, I've done my little portion of my process and I want to share my CPU and give up. And that's really why we need a timer interrupt. So, like I've said before, the key commands that we're looking at in terms of sharing or making use of this timer interrupt to go to sleep are the time delay, hour, minute, second, millisecond. So you delay for a specific amount of time. And this OS time delay for a set number of clock ticks. The main difference between these two is this is a specified time. The first one's a specified time, so it's going to be try and do a second or as close to, depending on the resolution of what you set up in your config files. This one with a specified number of ticks, this is actually a relative time. You don't actually know exactly how long your time delay is going to be. The reason is shown on this slide. So this is taken from the OS microCS manual. And the idea is that you can have the time delay n, you delay till the next number of clock ticks. So let's just walk through this slide. What I have is, at the top, I have running my interrupt service routine. So this interrupt service routine runs regularly, and it takes a small amount, the CPU for a small amount of time. After I've run my interrupt service routine, my OS goes, okay, run the highest priority task. So it runs, process 1, then it will run process 2, going through my list of ready tasks. Eventually you get to this low priority task, and it finally gets the CPU after a certain amount of time. Now suppose at this point in time, right after the end of this task, it wants to share the CPU. What it does is it calls this function here. So it calls OS time delay with for 2 clock ticks. So when does it wake? So it wants to wake 2 clock ticks later. But it's actually, what happens is, okay, carry on. Next interrupt service routine, we run high priority tasks. Because we're delaying this, this is sleeping for 2 ticks. This process here is asleep at this point. Then at this point in time, what happens is, let's call this process 4. Right here, process 4 joins the ready queue. So it joins the ready queue. What does that mean? It means that the OS can now pick which process it wants to run. And in this diagram, it so happens that this process is the only one that wants to run, so it runs immediately. So overall, if you can compare the time between 2 ticks, is the time from the first tick to the second tick, but the time that your process runs to when it runs again is actually less than 2 ticks. So you can see that this time is a relative time, but what it's important to do is it allows us to synchronize to our interrupt service routine. Okay, note that it doesn't necessarily have to be, it can be less than 2 ticks, it could also be no more than 2 ticks. Can anyone suggest how it could be more than 2 ticks? Yeah, so imagine that this didn't exist. So this low priority task started here, and then call the OS time delay 2. It joins the ready queue here, but at this point you run several high priority tasks, then it enters at this point in time. Right, so that's just to get you to know the idea. Right, why is this important? Well, this is all to do with our task stats. It's all about our synchronization. It'll come into play later on. But first I want to introduce what the idle task does. So the idle task runs when no other task is ready and it is the lowest priority. So those two things go hand in hand. And so if I look at my timing diagram, at all this point in time I run idle. In all this point in time I run idle, and so on. What does the idle task do? So at first, well, the key function as far as we're concerned is it increments this OS idle counter. Just a register which is incrementing forever. It'll loop around and increment over time. Okay, what else is around it? We've got OS enter critical and OS exit critical. So the idea here is that this OS idle counter, that's a global variable. Why? Because obviously this task, the idle task needs to access it, but also your task that's going to compute the statistics using this counter is going to have to access this same variable, so it has to be a shared global variable. If you're sharing a global variable, you don't want one to read, one to write, and them to read and write the wrong thing, or to corrupt your data. So we're protecting it in the idle task and by entering the critical section. This critical section, what it does, it will ensure that the CPU remains fully focused on this task, which means it will disable interrupts. So here I disable interrupts. At the end, I enable interrupts. Now, technically, being picky, technically I should say that this doesn't disable interrupts. It first stores interrupt status, then it disables interrupts, and this doesn't enable interrupt, it restores status. Can anyone suggest the difference between disabling interrupts and enabling interrupts versus storing the status, disabling interrupts, and then restoring the status? Sorry? Yeah, it doesn't, sort of. So it's not only pending interrupts, imagine that a first task has, someone else has disabled interrupts, and then you come along and then you disable interrupts as well, so you don't make any change. Then you come along and enable interrupts, and the other guy hasn't enabled them either. So you can actually muck things up that way. The last thing that it has is this idle hook, which allows you to, as a user, to add any random code should you wish to kill some time. So when designing a real-time system, we have to know our CPU usage. Suggest why. Can anyone suggest why? Let's put this another way. If I've got 100% CPU usage, are we happy? No one's happy. I've got 99%. You're not happy. Why are we not happy? One of you two. But if I don't have any more tasks? Yeah, it's true, I'm running a risky thing, running at 99%, but there's more than that. Is at some point in time might be 99%, but because I've got this regular processes happening with different periods, at a different point in time I might go over 100%, and therefore I might not be able to run my processes. And there's some various theories. There's some theory which says basically if you have 69%, you're good. And that's a rule of thumb if you want to go by it. So the statistics task collects the data when tries to work out how much of our percent is idle. So what does it do? It runs once every second and updates our usage counter, which is another global variable, OS CPU usage. Now you can access it from any task, and that's because some other task might want to say, if I've got this much usage, then I can run, or if I want this much usage, then print it out to the screen, or print it out to your 7-segment displays, if you would. So in terms of how this works, the first key is that you run a function called OS.init, and it runs from the first and only task running. And this is pretty critical, that we run it right from the start. And this is because this task is trying to basically configure how many clock ticks you have in a second. And if you imagine, if you have other processes, they might take the CPU for a section, and you might get the amount of CPU usage per second a little bit wrong because it's not idle. The idle count is not increasing over that time. So, looking at the code for this function, the first thing we do is we run this OS time delay 2, and this allows us to synchronize to the timer interrupt. And because from the diagram I showed you earlier, you should be all happy with this. What's happening is, at some point, some high priority task calls OS.init. Init. Then it's going to go to sleep, and it's going to wake up straight after the interrupt. Now, obviously, some stuff can happen before then, even though it's the first function you're running. The OS they're going to set up various things for your start task, which runs. So we synchronize it to the counter. Then what we do is we say enter critical section, because again, this thing is a shared variable. Start off our counter at 0, wait for the OS ticks per second. So this is something that you can specify in your config file. So it might be 100 ticks per second. I think that's what it's naturally set up to. So you delay for 1 second and then say, okay, what is the new value of my counter? And that's the amount of clock ticks I have per second. So it's all rather trivial, and that will configure how many ticks you have per second, which you can use to determine usage. Walking through this in more detail, which I hope you can roughly see, but I'll highlight the main points anyway. So this is your main code, and the main code does basically simple things we call OS init, which you should be familiar with, is just initializing your operating system. You create your start task, which is creating the first task that runs in the operating system, and then you say, go, operating system, go. Okay, your first task, what we do is we call OS stat init straight away, which I've just said, and then we hit this OS time delay 2 and delay for 2 ticks. At this point in time, you've got another task which runs, which is your task stat, which is actually started because you want to run your statistics task. You start this in your main program, and it runs a few lines of code and just says, should I start collecting my stats yet? And the answer is no, don't collect your stats yet, so go to sleep. Then after your 2 ticks, then like I said, you initialize your idle counter to be 0, wait for a second, see how many ticks you've had, store this in your global variable, keep that forever, then you can continue running your normal code, and every now and then you compute statistics. So that's all easy. Just one quick question. Why do I need 2 ticks? Why do I do OS delay 2 here? Why can't I just do 1? Can anyone see why? So, going back to my ever so useful diagram, imagine I call OS stat init right here. At this point I call OS stat init. I immediately get a timer interrupt, right? When's it going to wake? It's going to wake straight away afterwards. Then what's going to happen is it's going to start counting. But if you notice, there's actually another task which hasn't had a chance to run yet. So this task, all it's doing is checking, should I start collecting statistics yet? It does a trivial thing, but that trivial thing will take up however many clock ticks. So that will mean that your idle counter, which is running as your lowest priority task, will miss a few at the start, and it'll get its number slightly wrong. So it's just a bit of care in terms of synchronization. Another small caveat is that if you've got 100% CPU usage, then the task stat, which measures your current usage, it will never update your global variable. And if the global variable is initialized to 0, then whenever you check the global variable, your usage will always be 0. And because it's lowest priority minus 1, you can see that it's never going to take priority to check. Okay, how do we compute usage? So this is really simple. The difference between, so if I have a certain amount of time, if I count up to a whole portion of it, if I then am running tasks for a portion of it, then my idle count's only going to be a section of it. So the difference between this section and the whole lot is the amount of time you're idling. If you want to convert that to a percentage, which is generally more useful, you convert the count that you've measured divided by the max count. And then the reason why they've done this manipulation is that this function is going to be an integer division. So if you divide an integer division of a fraction, you generally get 0. So, 4 divided by 5 is equal to 0, remainder 4. So getting 0 all the time, or 100% usage, is not correct. So instead we just throw in the algebra, stick the 100 inside. Unfortunately, then you can potentially get overflow, so we do a division beforehand. So this is just moving the 100 to the bottom. So we first do this division of our max counter, and then we can work out usage. What else is there to say? Yes, so note that, again, this is integer division, so there still can be some accuracy lost, but you can imagine this is a very big number, your idle count max. So losing a few bits at the end, you're not really going to care that much about. And similarly, losing a few bits with this division, you're not going to care about. I've just copied the actual statistics task here. Again, so this is first check if you're ready, time delay, I'm missing a semicolon here. Close bracket. Then you just run this task, enter the critical section, check your idle counter, and then compute your CPU usage. Note that another slight advantage of pre-computing your idle counter max is you can do it outside of this loop. By doing that, then you don't have to compute it inside. That saves a few CPU cycles. Standard code optimization, the kind of thing that you should be familiar with when you're writing any code. Okay, so if we want to actually measure the timer interrupt overhead, note that your interrupt service routine takes some time of your CPU as well. So if I have my interrupt service routine, and here I've got an idle task running with 2 interrupts per second, so I got 500 milliseconds between interrupts. You can see that my idle task isn't actually counting every clock cycle. It's missing when they've got a running interrupt service routine. So how do I estimate the size of this interrupt service routine? The easiest way is if I run a second idle task. So I run an idle task 2, okay, actually not a second, a different instance, and you run it with, say, 1 interrupt per second. So then with 1 interrupt per second, you'd get the same interrupt at the start, but you would miss the second interrupt. So each one of these, this is going to return idle 1, this is going to return idle 2. The difference between idle 1 and idle 2 is going to be this interrupt service routine call. So we just work out the number of clock cycles are spent in that interrupt service routine. And this is all that is highlighted here. So compute the difference between a 1 Hz timer and a 2 Hz timer. And then what the difference is the size of the time for an ISR. The total time is going to be the time for a 1 Hz plus your ISR. So your total time is from here to your next stop period. And then you can see, you can generalize this approach, and this is something that you have to do in the lab. Has everyone done this in the lab? No. Some people have, some people haven't. You generalize this idea to 100 Hz and 1000 Hz. It's pretty trivial if you need to draw out the diagram. Slide 17 of 14. Right. What was next? Again, talking about the lab, just giving a little bit of hints on the final sections. Now, to my knowledge, a handful of people have completed this, but just for those who haven't. So what you're asked to do is you're asked to create brightness level, and you're asked to do this with pulse width modulation. Now, you have covered pulse width modulation, I believe, with Andy. So you should be familiar with it. But it just suggests a really trivial approach, which is you have an accumulator. If your accumulator passes some threshold, you output a 1. Otherwise, you output a 0. And what happens is your eye will kind of average out the amount of time it's on and off, and that will translate to some form of brightness. If you wanted to write it all down, you can easily work this kind of thing out. So if I want a brightness of 12, then if I look at over a period of time, so every iteration, what's the value of my accumulator? So after one iteration, I add my brightness. So this is just adding 12. I add 12. You can write this out yourself for any kind of brightness. When you've passed 32, you compute the result modulo 32, or you subtract 32. So 36 changes to 4. Whenever you've crossed 32 again, you output a 1 instead of a 0. So how does this work out? Well, so this just carries on, adding 12, all trivial. You notice that here I've got 4 in my accumulator, here I've got 4. So you can kind of look as this being that pattern of your LED output is going to constantly occur from now on. So this pattern is high 1, 2, 3, and it's low the rest of the time. So 3 over 8, and which is equal to, what is it? 4 over 8. 3 over 8 should equal 12 over 32. Is that right? Yes, it is. My maths is not that bad. Right. So yeah, so that you get the equivalent brightness value, but just by having this accumulator. And you can test it with any number if you want. So the second section, which tries to build on it, is you try and create this wave pattern where you try and get the brightness to go up and down slowly over a set of each of your LEDs. The way it's suggested to do this is to create some kind of triangular wave pattern. So you can imagine if you have your triangle wave, this is something that goes up and down in brightness. So I've got my brightness going from 0 to 32 and back down again. Over this time period, I output using PWM the given brightness value. And then your eye will see given brightness value increasing and then decreasing over time. How do you implement this function? Well, it's actually trivial. So I've written the code to do it. If phase is less than 16, you return 2 times phase. Let's just check this out. So if I start off with phase equals 0, 2 times 0 is 0. So brightness is 0. Phase equals 4. 8. 8. You get 16, so on and so forth. 12. 12 times 2 is 24. 16 times 2 is, well, it's 64 minus 2 times 16, which is equal to 32. 20 is 64 minus 2 times 20, which is equal to 24. So you can see how I'm going up and down this ramp just by changing my input to this function. This is all I'm changing to create a triangle. And then if you want to create this into code, into your final thing, the only thing you have to add is, okay, work out my brightness value and then output it for a chosen period of time. So output it for this amount of time you have to choose. Now, how do you do that? You might want to put, say, a for loop around this section, and every time you're around that for loop, then you using the previous pulse width modulation scheme, your current brightness. Then you can just add +4 to my phase, modulo 32. So that's saying whenever I get past 32, I'll subtract 32. And that will just loop around my phase, or that will just, in other words, it'll loop around showing my increasing and decreasing phase. That'll allow you to create your triangle wave and your brightness, and you can change this from 4 to 1 if you want a more smooth brightness function. Okay, so that's basically the idea of the code. Right. Back to the main notes. Two processes communicate. Inter-process communication is basically key whenever you're doing any kind of real-time operating system, because tasks or processes, you have lots that run in parallel, but realistically they need to communicate somehow. Quite often it'll be waiting on data. So someone's updating some shared variable, the next process wants to grab the updated shared variable. You might want to pass information. You've got two processes that do different functions, they communicate with each other. And you lead to two different types. You typically have this blocking where you wait for your response, or non-blocking where you just update your function, you update your global variable and then continue doing what you want. And it's the non-blocking which is generally dominates, and the functions that I've shown you today are non-blocking. They update the idle counter and then give it up. So you have different types of processes, and we got different ways of performing this communication. So we can have shared memory or message passing. So you can, depending on your CPU and operating system, you might have special parts of memory or special bits of hardware that will allow dedicated sharing between processes for a faster system, but largely you have this shared memory. So all processes have some memory in common, or they access the same global memory, and you have to cooperate to avoid destroying and missing messages. So this is true both on a bus and within a single CPU. So you have processes on a bus, so it wants to write to this memory location. At the same time, the bus has to close off from CPU writing or looking at that memory location, and vice versa. So that's trivial, but I should say that in this course we're more concerned about this being process 1, process 2, process 1, and this not being a bus, this just being shared memory. If the exact same thing applies. We can't overwrite the shared memory or things can go wrong. And the problem is known as race conditions in shared memory, where you have both CPUs trying to write to location. So what happens is you can, in this protocol, you have to first say, check a flag, am I allowed to read it? Then if yes, then you can write to it. So the first CPU checks it, says, oh, it's free. The second CPU comes in, overtakes it, or a second process gets preempts the first, says, okay, I can write to the shared memory as well. Then CPU 1 writes to the shared memory with a value, and then the CPU 2 just overwrites that value, completely ignoring whatever CPU 1 has written. So you can imagine the code here was to add 1, and this was to do something. What you really want is to do something, then add 1, but what happens is you do something, write something, ignore what that something is, and just add 1 to the initial value stored in the memory. Yeah?
Let me only like the CPU one to capture the bus.
Yeah. Well, so, I mean, what could happen in this case is that CPU1 captures the bus and reads. CPU2 catches the bus and reads. CPU1 writes, catches the bus and writes. CPU2 catches the bus and writes. In that case, still, your CPU2 is not reading what CPU1 has written, right? So whatever CPU1 has written is just lost, and you can get incorrect data.